Hello, in this video I'll be going over some questions involving Newton's law of gravitation. So basically what Newton discovered, other than his law, his first law pretty much, F equals ma, he also discovered that objects in the universe, such as two planets pretty much, so you have planet A and you have planet B, there will be a force of gravitation attraction between the two bodies. So there'll be a force going this way and a force going this way to attract the bodies together. And what he discovered was pretty much what is known today as Newton's law of gravitation. He discovered there's attractive force between two bodies, and it's actually equivalent to F equals ma. So while force is equal to mass times acceleration, force is also equal to a constant multiplied by the product of two masses divided by the distance squared. So this is Newton's law, Newton's second law of motion, and this is Newton's law of universal gravitation. So what does this actual formula here tell us? Okay, so let's just break it down. So F is force, G is a constant. The constant's number is 6.67 times 10 to the negative 11 newtons meters squared divided by kilograms squared. Okay, that's a constant. That number is constant. It's Newton's gravitational constant. M is the mass of the first body, and lowercase m is the mass of the second body. So let's say, just for an example, we think of two planets, right? Let's stick with planet A and B. And if you had the distance, let's say the distance is, let's make it something crazy. Actually, no, let's not make it crazy. Let's just say they're 100,000 meters apart. Okay. And the mass of planet A, let's say mass is 3.0 times 10 to the 40 kilos. And let's say the mass of planet B is 4.0 times 10 to the 35 kilograms. You could work out what is the force of gravitational attraction between the two bodies. So let's use our formula here. So F is what we're trying to find. G is our constant, so I'm just going to write the formula real quick. So I'm going to have F equals G multiplied mass 1, mass 2, divided by the distance squared. So when we write this, we write Newton's gravitational constant, which is 6.67 times 10 to the negative 11. Just leave the units out while we're doing the math. Multiply by the mass of the first body, so let's just say this is capital M. Multiply by 3.0 times 10 to the 40. Multiply by the second mass, which is this one, 4.0 times 10 to the 35. Divide by the distance squared. So our distance in SI units is 100,000 meters. Just leave the units off and square that. And if we put that into our calculator, we'll get the force of attraction between these two planets. So just putting that into our calculator, 6.67 times 10 to the negative 11 multiplied by 3.0 times 10 to the 40 multiplied by 4.0 times 10 to the 35 divided by 100,000 all squared. And we get 8.004. That's rubbish significant figures. If it was like two significant figures, just write it as 8.0 times 10 to the 55 newtons. But that was just an example. So in this video we'll be doing questions like that. This is just pretty much only 3 questions will be covered in this video. There will be more parts coming though and be uploaded to the channel. Alright, let's take a look at another example and see if you can have a go at it. Alright, so this just doesn't work for planets. This works for any whole bodies pretty much. So just any two objects. So have a go at question 1. Two students are sitting 1.5 meters apart. one student has a mass of 70 kilograms, while the other has a mass of 52 kilograms. What is the gravitational force between them? So if you want to have a go at this question, feel free to pause the video and have a go. Alright, so straight off the back, what do we have? We have the distance between the two students, okay? So we have student number 1 here and student number 2 here. So I'm going to make this student a bit smaller than the first students, because this one over here is heavier than this one by like 18 kilos, I think. Yeah, 18 kilos. Alright, so this mate here, he's 70 kg, and old mate here is 52 kg. Alright? The distance between the two is 1.5 meters. Excellent, we have all of our stuff in SI units. So all we got to do is use our formula that Newton gave us. So we have F equals capital G multiplied by the first mass multiplied by the second mass divided by the distance all squared, okay? Big G is 6.67 multiplied by 10 to the negative 11. Just leave the units off for now. So we're going to plug that number into this formula, and we're going to plug that number into the formula, that number into the formula, and this number into the formula. Okay? Oh, I just rubbed out that person's head. He can have a blue head. Alright, plugging that in, so we're going to have F is equal to 6.67 multiplied by 10 to the negative 11, multiplied by the first mass, which is 70 kg, multiplied by the second mass, which is 52 kg, divided by the distance squared, so 1.5 all squared. Putting that into our calculator, 6.67 times 10 to the negative 11, multiplied by 70, multiplied by 52, divided by 1.5 all squared, and we get 1.08 times 10 to the negative 11 newtons. Now notice, when you stand next to someone in real life, you don't feel a force pulling you towards you. That's why this force is so small. But there is a force of attraction. It is very, very small. Look at the index here. It's a negative. That means it's like, it's going to be 0.0070 zeros. It's so small and insignificant. Okay, but obviously we can increase this force if we increase the mass, and obviously we also can decrease the force if we increase the distance. So let's just take a look at our formula here. So I'm just going to move all of this into the corner for a second and just make that a bit smaller. Come on, select all. So let's just take a look at our equation here. So F equals Gm multiplied G times the mass 1 times the mass 2 divided by the distance squared. If we increase the mass of one of the bodies, so we increase this number, obviously the force is going to increase. If we decrease the distance and make this number bigger, obviously the force is going to decrease then. Mathematically and logically we can see that. If you bring two objects closer together, there'll be a greater force of attraction. If you pull two objects further apart, there'll be less force of attraction. As well as if you decrease the mass of one of them, the force will decrease of attraction. But if you increase the mass of something, its force will increase. Okay, so that's just a little side topic. Let's move on to the next question. Alright, what gravitational force does the moon produce on the Earth if the center is 3.88 times 10 to the 8 meters apart, and the moon has a mass of 7.3 times 10 to the 22 kilograms. So if you're in the Queensland syllabus, the rest of the information to solve this question is in your data book, I believe. So feel free to have a go at this question if you're feeling brave. Otherwise, just wait for me and I'll start solving it. Alright, so what are we thinking? So we just imagine the Earth and the moon, okay? We've been given the distance of centers, so we've been given the distance they're apart. So we have 3.88 times 10 to the 8 meters, okay? We've also been given the mass of the moon. So mass of the moon is 7.34 times 10 to the 22 kg, okay? So far everything's all nice because it's all in SI units, alright? Alright, let's see if we can do our formula. So F equals G M M r squared. We have a mass, we have our gravitational constants, and we have a distance. What is this mass? So the mass of the Earth. So if you check if you're in the Queensland system, Queensland syllabus for physics in Australia, in your data book at the very back is the mass of planet Earth. The mass of planet Earth, I believe off the top of my head, is 5.97 times 10 to the 24 kg. Okay? Or you could just actually let me just double check that real quick. I believe it is. Yeah. Or you could just write it as 6.0 times 10 to the 24 kg. Okay? Depending what system you're in. Okay? In America, you might use 6.0 times 10 to the 24. In Australia, though, we use 5.97 times 10 to the 24. Alright, so that's the situation we have. And this here is the mass of the Earth. So, mass of the Earth is 5.97 times 10 to the 24 kg. Okay, that means we've got everything to find our gravitational force. So plugging all this into the formula, we know that G is 6.67 times 10 to the negative 11. That's our constant, that's our big G in our formula. So F equals 6.67 times 10 to the negative 11 multiplied by the first mass, I'll just choose Earth, 5.97 times 10 to the 24, multiplied by our second mass, which is the mass of the moon, 7.34. Oh, we're running out of room. I'm just going to move all this across real quick. Times 10 to the 22. Divided by our distance squared. Alright, and then you plug that into your calculator, and you should get, plugging that in, you should get 1.94 times 10 to the 20 newtons. Alright, cool. That's our